Hi, I'm Zhou Wenyu, and I'm presenting SAMO, Optimized Mapping of Convolutional Neural Networks to Streaming Architectures, which is a collaboration work with Alexander Montgomery Cochrane and Christos Boganis. So deep learning models have obtained a great success over the last decade, and one of the representative models is the convolutional neural network. In the software domain, designing a CNN is becoming much more convenient than 10 years ago thanks to the popularity of the frameworks such as PyTorch and TensorFlow. However, deploying such a CNN onto hardware is still challenging. Let's consider a few applications of the CNN here. If we want to deploy a CNN onto a drone, probably for its navigation, the first thing we need to consider is that the drone has a limited battery capacity. Therefore, we need to make the hardware very low power. On the other hand, if the CNN is deployed on a self-driving car, latency is now the prime concern, as we want the system react to any potential danger as quick as possible. And for a data center, maybe we are more interested in its system throughput. Therefore, we need some tools to help us design the hardware for CNN, and there are a few requirements we need to consider. Firstly, we want a tool to generate scalable hardware, as we are dealing with applications from drones which have very limited resource to data center which owns a lot of computing resources. Secondly, we hope the tool can map the CNN onto the hardware in an automatic and end-to-end way, so that it can free software machine learning engineers from the hardware background knowledge. Finally, this kind of tool should be efficient in terms of optimizing the matrix trade-off, such as accuracy, latency, throughput, and power. One type of work can satisfy all three requirements, which are the CNN FPGA2 flows with streaming architecture. The slide here lists several examples, which are FIM from Xilinx, HLS4ML, which is from the FastML lab, and finally the FPGA ComNet, which is designed by our research group. Let's now have a look how this type of work satisfies the requirements that previously mentioned. This type of work chose the FPGA as a platform for CNN deployment, as it is much easier to have the flexible and scalable hardware design on FPGA than ASIC. The hardware is also generated in a very automatic and high-level way. So, in the existing works, they use Python scripts to generate C++ templates for hardware designs, and these templates are then compiled into HDL code through the high-level synthesis tool. This kind of work also employs the so-called streaming architecture or data flow architecture to have efficient hardware designs optimized for latency, throughput, or power. In the streaming architecture, each layer in the CNN is mapped to a custom computation kernel tailored to the characteristics of the layer, and the overall CNN computation is achieved by pipelining these kernels. This architecture has a simple control logic, and the player hardware customization allows us to make many design choices. Therefore, streaming architectures have higher throughput and energy efficiency compared to equivalent systolic array designs. Well, the player hardware customization is a good thing for improving the efficiency, but it also brings out an open research question, that is how to explore the large design space. Therefore, we present the SAMO framework. The contributions of our work include: we propose a unified framework that is able to interact with the existing CNN FPGA2 flows with streaming architecture. That includes FIN, HLS4ML, and FPGA ComNet. We can help them efficiently identify optimal designs. To make it happen, we introduce the hardware description graph, which is a generalized representation of the optimization problem. We also explore and compare three different optimization methods, which are brute force, rule-based, and simulated annealing. Let's now talk about this in more details. In order to address the optimization stage of mapping CNN models to stream architectures in a unified manner, we found the first challenge is that HLS4ML, FPGA ComNet, and FIN, which we call them as backends, have very different hardware implementations for the CNN. The two figures at the left side compares how a convolution layer is computed in FPGA-COMNET and FIN. We notice that in order to solve the optimization problem, it's not necessary to expose the hardware implementation in so many details. In fact, we only need to focus on the common characteristics of these backends. We are interested in that on which dimensions the computation is parallelized, what is the benefit on performance, and what is the corresponding cost on resources. In SAMO, we offer the translation from the backend-specific hardware implementation into the proposed generalized hardware representation, which is the hardware description graph, and that provides the abstraction we need. For the hardware description graph, at the whole graph level, it provides the information on how the data flows through the CN model, what is the dependency in computation, and what is the amount of data communication between layers. It also provides the specifications of the target FPGA device, including the maximum resource available on chip, the bandwidth of off-chip memory, and the time of performing a bitstream reconfiguration. At the graph level, SAMO introduces a partition method to generate high-throughput designs by reconfiguring and time multiplexing hardware kernels on a single FPGA device. Therefore, an optimization variable here is to find out the appropriate position to cut the graph into parts, which is denoted by the symbol C here. Each node in the hardware description graph corresponds to a computation kernel in the stream architecture, and the node stores the corresponding resource and latency models. These models can either be provided by the backend developers or by us. For each node, we are able to find out the unrolling factors at input channel, output channel, and kernel dimensions, which are commonly used across the backends. Finally, with the hardware description graph, we can abstract the optimization problem into the following equation. Now we have obtained this generalized and abstract representation of the optimization problem. We explore three different methods to solve it in SAMO. The brute force method simply enumerates all possible values of optimization variables. Each of them is evaluated of the objective function and identify the optimal one. The method guarantees the identification of optimal design at the cost of a very lengthy optimization time for large networks. The simulate annealing method is the well-known stochastic algorithm. In each iteration of the optimization, this method performs a random change to the optimization variables and evaluates its objective function. It may even accept a new design, even though the new design is worse in the objective function than before, which helps to escape from the local optimum. Finally, we have the rule-based method, which greatly improves the slowest node in the graph, in addition to a set of heuristics. The rule-based method is a deterministic algorithm and is very fast to run compared with others, but is highly likely to be trapped at local optimal because of the greedy optimization. Empirically, we found the brute force, simulate annealing, and the rule-based method is suitable for small, medium, and large-size networks respectively to achieve a good balance between optimization time and optimization quality. Let's have a look at the final performance that our framework can achieve. We compare against example designs provided by the authors of each backend, where the optimization problem is solved by manual tuning. From the table, we can see that overall, SAMO achieves the same or higher performance by up to 20 times on a set of CN benchmarks. It shows SAMO can serve as a powerful tool for CN accelerator designers, and we hope it can be helpful for the whole community. If you are interested in our work, you can find more details by reading our paper and have a look at our code. Thank you for your attention.